Hello everyone, my name is Ming Lu. Today I am going to show you my research on wireless charging and the design of 3.3 kilowatts wireless inductive power transfer system. The application of my research is wireless charging for electric vehicles. Specification of the design system is shown in this table. Output power is 3.3 kilowatts. Output DC voltage ranges from 300 watts to 400 watts. Input DC voltage is 400 watts. Transfer distance is 10 cm. The goal of the efficiency is larger than 95%. The topology of the system is series topology, which means the resonant capacitors are connected in series with the coils on the primary side and secondary side. The system is analyzed with a simplified circuit model. Full-bridge inverter with DC input voltage source is modeled with a sinusoidal voltage source. Passive rectifier and the load are modeled with an equivalent resistance. Structure of the coil is a circular planar winding placed above the square ferrite plate. Material of the ferrite is N95. Air gap between the transmitter and receiver is 10 cm. The self-inductance of the coil is selected based on the operating frequency range and the requirement for transferred power. Calculation shows the range of the self-inductance should be larger than 135 microhenry when coupling coefficient is between 0.2 and 0.25. Turns number of the finalized coil is 19, with 150 microhenry self-inductance and 0.24 coupling coefficient. PVC plates are used to fix the ferrite plate and the winding. The dimension of the coil, including the PVC plate, is 300 mm by 300 mm by 25 mm. The voltage stress of the resonant capacitor is a concern. To transfer 3.3 kilowatts out power, the voltage stress on the primary side cap is 1.35 kilowatts and 850 watts on secondary side cap. Film capacitor is chosen for reliability consideration. However, because of the decrease of voltage rating at 100 kHz, capacitor bank is used to handle the voltage stress. The inverter is operated with complementary gate signal, and by selecting the proper operating frequency range, ZVS turn-on is achieved for the inverter. Switching frequency is tuned to get 3.3 kilowatts when load resistance or coupling coefficient changes. Here is the hardware setup. This is the primary side inverter. This is the transmitter coil and receiver coil. The air gap between them is 10 cm. Here is a resonant capacitor. This is for the primary side, this is for the secondary side. So this is a waveform from the test. The first waveform is the primary side voltage. Second one is the primary side current. Third one is secondary side voltage. And fourth one is secondary side current. From the waveform, we can see that on the primary side, the inverter can achieve ZVS turn-on. That's my video nuggets. Thank you.